Als nächsten Referenten haben wir aus London wieder dazu geschaltet, Ricardo Petraco. It's about artificial intelligence to guide physiological data interpretation. So something that we will be confronted with in the future. And so we are very excited to see what you can tell us.
Many thanks. Thank you again for this invite. I will cover this topic, which, as you said, is very fashionable, very in vogue. And we will aim to discuss here how this probably will impact and is already impacting our cath lab activities. Excellent. So AI things are very common these days. In every cardiology meeting, you're going to see more and more topics on it. They're very important, very common, very fashionable. But what you really have to understand is whether we really need it in the cath lab, and for which type of tools and decision-making, artificial intelligence will really make a difference. So hopefully I'm going to discuss here a few glossaries of AI terminology, which is useful for us to understand how it works, difference between simple algorithms that already exist in computers and already help with decision-making and AI systems, and discuss examples of potential AI applications in physiology and beyond. So the first thing for us to know is that computers have already been helping us to make decisions for a while now. And it's very simple for us to program computers to follow some instructions. So for example, if I want to tell a computer to guide us on a fixed cutoff for FFR, I can simply write a computer code that if the pressure ratio is less than 0.8, it will display a sign there for you to stent it. So that's very easy to understand and very simple to implement. If I get things a little bit more complicated, like from the IFR calculation, it's nothing more than an algorithm that I've just put like a snapshot of it here. I ask the computer to identify each cardiac beat, within each cardiac beat diastole, and within diastole to create a pressure ratio. Again, not very complicated, and we can simply follow that with a simple or relatively simple algorithm that already exists. Now, if we go a little bit more complex in decision making, if I want, for example, to start looking at whether a lesion is focal or diffuse, I can, again, tell the algorithm, the computer with specific learning properties and say, if there is more than 3 units of IFR drop in a given segment of the vessel, the computer will call it local and tell me that this is potential an area to stent. So again, for that, I do not need artificial intelligence, and is a very simple code to write based on pressure and time. Now, things get a little bit more complicated when we start involving more complex decisions that involve a clinical output. So, for example, I want to know where I should stent this lesion here, this vessel, based on that plot. And this is a little bit more tricky because you don't use just the pressure drops or the definition of focal versus diffuse. And if I tell the computer simply to tell me where the pressure loss is focused, it will probably get it wrong and it will tell me to stent 2 segments, and in reality maybe the 2 segments do not need to be stented. So that's really when artificial intelligence comes into its place, which is to help us in more complex decisions which are not easily explainable and involve multiple variables. So for us to understand the terminology, as I said, a computer algorithm is a very simple definition of a finite sequence of well-defined computer implementable instructions, typically to solve a class of problems. So the computer cannot learn from it, but it will follow what you say. Artificial intelligence, on the other hand, is a collection of computational concepts that can be summarized as the machine's ability to generate learning by itself as it uses the technology. And machine learning in specific is a type of a collection of algorithms that let the machine learn as it uses as it goes through the process. So for example, our spam box is a classic example of a machine learning code in our email box that as soon as you start deleting emails from your account, the machine starts learning that that email is not of your interest, and in the future it will start deleting it automatically. Now, what is really comes into practice for complex decisions, what we call deep learning, and particularly with layer neural networks. So for instance, here you have a data from a pressure loss or pressure drop, a pullback, that goes into what we call the input layers. Of course, I won't have time, and I don't even have the capacity to explain in details how this complex convolution neural network works. But at the end, the final result that comes with a clinical decision. The important bit here is that this neural network has to be trained by experts to provide us with a gold standard. So deep learning is a complex and deep branch of machine learning, which is part of a wider umbrella of what we call artificial intelligence. And this is really important for us to understand the difference between each technology. So let me start now with a clinical problem. And I'm going to ask you, what is the FFR here? Everyone is going to look at the screen and say it's 0.86. And then I show you the drift check there, and it's 0.98. So, you know, if you overlook this very quickly, there is no significant drift, and I might say that this is a negative lesion. Now, if you pay a bit more attention to it, if you're a human, you can look at it and say that it's actually there's pressure dumping, and we should not really look at that value reliably. Now, the problem is, we know the mechanisms, and we know if we reposition the guiding catheter, it will turn up to be a positive FFR. The problem is identification of a normal pressure waveform is essential for adequate physiological data interpretation, but we all fail to consistently identify PA pressure dumping. And not just us, you, it's us, the community, experts, general physicians. Now, it's quite complicated. It can be done, but it's not as easy to implement a simple algorithm that tells when the pressure is dumped. And therefore, artificial intelligence here comes in a very good position. There has been work done by our group on trying to identify waveform abnormalities with artificial intelligence. And in a very simple summary, we got experts to label traces as normal, dumpoid, or mildly dumped, and very dumped. And we train the machine with training data sets in several thousand beats to label this according to the expert guidance. And as you can see here on this typical chart, the efficiency of the machine with time is very high, and there is an agreement very close to 100% between the computer machine or the artificial intelligence embedded within the algorithm and the experts, which is superior to the agreement between experts themselves, which really shows how really the machine has learned from the expert labeling of the traces. So in this case here, we have another issue, which is, as I mentioned before, where you're going to stent this lesion based on this pullback. It's very difficult to write a simple algorithm to do that. And again, we have tested here where the artificial intelligence can help us to make that decision. And the process is very similar. You get a lot of traces. One of the key things about deep neural networks and artificial intelligence, it requires a lot of data to train a network. In this case, you've got more than 1,000 IFR pullback traces. We got expert human analysis from multiple centers, and they find not only whether the lesion was appropriate for PCI, but offering a PCI strategy. And we compare that with a computer algorithm. And here what you see in yellow is the graders, the experts grading where we think the lesion should be stented based on the pullback data. We have no access to the angiogram here. This is purely based on the pullback data. And what is really amazing to see is that with time, there is a consensus between the operators, is that the computer learn very similarly to what the consensus between the operators would be in terms of PCI guidance, and tell us to put the stent in the very same position that we would put. Obviously, there are many benefits of using computers. There is more objective and uniform classification. There is little noise or variability with 0% misclassification to pressure wire drift, because of course the computer can also tell whether the wire is drifted, and is 100% reproducible. If you show the same trace to the computer again, we'll give you the same answer, which is not the case with humans, as we obviously know. Now, where else can we look in the future and see where artificial intelligence is being applied? There's a lot of groups already working on IVUS and vessel sizing, particularly identifying the media and the lumen for vessel guidance. There's work on OCT and plaque characterization on trying to identify the types of lipids and whether there's a vulnerable plaque or not, based on histology and labeling from experts as well. And of course, there's data on structural heart disease and TAVI selection, particularly TAVI sizing and the type of valve given a 3D aortic root reconstruction. So there's a very exciting work that in the future we believe the computers will be able to tell us not only the type of valve that will match the patient, but also its size. So in summary, there are basic and complex computer algorithms already in place helping us to make decisions every day in the cath lab, but they are limited to pre-specified instructions, and they cannot learn by itself, and they're not very good for complex clinical decision making. So artificial intelligence via deep learning and neural networks mainly can potentially increase the complexity of computer-generated decision making, such as identification of damped waveforms, of selection of focal or lesions to stents. And I think that future cath labs will be obviously filled with AI solutions in the same way that iPhones are these days. Thank you very much for your time.
Dear Ricardo, Petraco, thank you very much for these impressive data. I'm really impressed to see how computers can help us to further improve the procedure and how to interpret the procedure and how to avoid mistakes during the procedure. And especially with the intracoronary imaging capabilities, I think we will have a very interesting future of what future studies will show us and how we will perform procedures in, let's say, 10 or 15 years. Since we are already a lot ahead of time, I'm afraid that we have to move on. We are looking forward to see what the future brings with artificial intelligence, and go back maybe to the reality and to nowadays with another interesting cases. Thank you very much, Ricardo.
Thank you very much for your invite. It was very nice to join you.
Good to have you. Thanks.